Good day, and you're all very welcome to this Saturday's presentation of the CNPS, which is a technical session presented by me, hosted by me, Ian Cowan. Today, we're delighted to have Stephan Gift back again. Stephan has talked to us a number of times. He's based in Trinidad and Tobago, and on a number of occasions, actually, he's given us most interesting presentations related to electromagnetic radiation and transmission and even superconductivity and that sort of thing. He has some very interesting novel ideas which have helped me actually in some of my investigations, I might say. And Stephan is sort of deprecating, if I may say so, the general tendency to use the Lorentz transforms between different frames of reference. He favors the Solari transforms. Well, today he's talking about something else. It's basically his work with regard to gravitation, and it's called A New Theory of Gravity, which he describes as containing 300 years of Newtonian gravitation. And it effectively converts classical Newtonian gravity into a quantum theory, which would seem quite specific, because sometimes these things are thought to be incompatible. So the theory mediates the gravitational force via the exchange of spin zero gravitons, and passes several tests, including perihelion shift, light bending, and Shapiro time delay. Now, that last bit doesn't surprise me at all, because Stephan is a researcher who, in my experience, has always been extremely cognizant of the necessity to meet experimental results. You know, you can sort of frame theories in the ether, pun intended, actually, without regard to whether they live up to experience. And you know, one can weave all these theories, but Stephan is always cognizant of the necessity of meeting experiment. And no matter how many experiments your theories conform to, and no matter how logical they may seem, if one experimental result contradicts those, they have to be abandoned or modified. So I think there's no better man to hold that concept always in mind. Now, let's see. So as usual, we'll welcome people coming in from the media, Facebook and YouTube. I haven't got any comments yet, so I'm waiting. Maybe they're coming in soon. We have a number of people in the green room already, and there's a private chat which they can engage in. So if people on the general media have a specific question which they don't want me to miss, because I'm likely to consider a lot of information as merely conversation between the participants, which you're most welcome to engage in, by the way. But if you have a specific question for Stephan, please do say, you know, specific question for Stephan, or don't miss this. So I don't miss it. And we'll put all those matters to Stephan to address. And when we're finished doing that, we'll go to the green room. And I think there are people coming in now, so we'll have a very good conversation, I'm sure, about this new gravitational theory. Right. I'm with your permission and the permission of the authorities here, I'm not going to waste time putting up the video on the funding mechanism again. You know, we're sort of coming up to halfway through the year. And just to remind you, though, I'll just say in a few seconds that we have this funding drive, which David Hilster has brought in again at the beginning of this year. It's basically intending to bridge the shortfall between the daily running expenses of the CNPS, running all these conferences and, you know, the software and so on. And he's made very considerable economies by getting rid of older software we had and bringing in newer software, which is more appropriate. But also the gap between the running costs and what we're actually getting through membership dues, which we're very grateful for. So there's an additional funding mechanism, which I think has reached about 55% of its goals. There have been very much favored contributions. Thank you very much for those. But there is a bit of a request that if you could go into fund.naturalphilosophy.org, fund.naturalphilosophy.org, and maybe if you haven't given a few dollars, would be much appreciated if you could do that. So, but I'll say no more about it. Today we're talking about Stephan's theory of gravity. So, Stephan, you're very welcome as usual.
Good morning.
And, thank you very much. So, I know we don't have any problems. You're a very lucid speaker, and you're always presenting your case very, very clearly, and you're always very patient with the people who are asking questions. We will endeavour to give you, as usual, an uninterrupted hour or so. It doesn't matter if it's more, if it's an hour and 15 minutes, or even if it's only 55 minutes. That's quite all right. But if in extremis something arises, and it hasn't actually arisen in my time, but if it arises that somebody is really completely confused and it's going to upset that person, he might just interrupt and say, sorry, that word that Stephen used, I didn't understand it. We might interrupt you, but it's very, very unlikely that we will do so. We'll give you the uninterrupted hour or so, and then we'll engage in a more detailed discussion. So what I'm going to do, Stephan, is I'm going to put your screen up, so you can put your slides up.
Okay.
And I'm going to put myself down, so the echo will go. And it'll be totally up to you now.
Are you able to see the slide now?
Perfectly.
Beautiful.
So if you need me, just call.
I will do so.
Yours.
Yes, sure. Thank you very much, Ian, and thank you for the opportunity once again to speak to this elite group of researchers and people involved in scientific work. I do appreciate the opportunity to speak to you about some of my work. Today I'm going to speak about a new theory of gravity. Although I use the word new, it's not the equation that I will present has been around, but I have developed it in a different framework. So that's why I have chosen to use the word new. So I guess you could just indulge me and allow me to continue to use the word new, even though the equation that I will demonstrate isn't exactly new. So a new theory of gravity is presented. A summary of the work. It contains 300 years of Newtonian gravitation and effectively converts classical Newtonian gravity into a quantum theory. I would say that it's not fully developed as a quantum theory, but I will explain why I say I believe it has the elements of a quantum theory. And it mediates the gravitational force via the exchange of spin zero gravitons. The general relativity, which is the accepted theory, talks about spin 2 gravitons. My work involves spin 0 gravitons and passes several tests, including the perihelion shift, light bending, and Shapiro time delay. So that's a summary of what I will present today. Now, I wish to start by going back to what is often referred to as the central problem of relativity. And I'm going here because I want to show the connection between work that I have presented here before and the work that I will present here today. So the central problem was to find transformation connecting two inertial frames, S and S prime. You know, that's the usual situation there. Let me just... I see something at the bottom here, Ian. Let me just, I don't know. There is something on my screen I'm seeing. I hope it's not affecting you. But anyway, I will continue. So it's solving this problem, the central problem of relativity. And Einstein, in solving that problem, Einstein used two postulates, the principle of relativity and the principle of light speed constancy, and he derived the Lorentz transformations, as we all know. And some of my work, which I've presented before, I've shown that I've come up, I prefer different transformations developed by Franco Sileri in solving the same problem. But today we're talking about what has happened with the Lorentz transformations. They led to four-dimensional space-time, and the concept of four-dimensional space-time as espoused by Minkowski. And the four-dimensional space-time forms the foundation of general relativity, which is a theory of gravity, and that's the accepted
Stephan,
theory of...
my sincere apologies.
Yes.
The little banner at the bottom of your screen that I think you may have been referring to is about sharing. At the right-hand side, it says hide. If you click that, you'll get rid of it.
I try that. Okay, good. Maybe I didn't. Yes, good. Thank you, Ian. Okay. So, Lorentz transformations, which we are all familiar with, they lead to the concept of four-dimensional space-time, which forms the foundation of general relativity. Now, Einstein's theory of gravity, which is general relativity, that equation that you see there, and I wouldn't try to read it out, is his well-known and well-famous field equation or field equations. It really comprises 10 nonlinear coupled equations. They are very nonlinear and difficult to solve. They represent gravity as curvature of space-time. And many of us still grapple with that concept, what exactly that means. I'm not sure if I have a handle on it either, but that's what the theory espouses. And I would say that a linearized general relativity involves exchange of spin to gravitons, which I was mentioning earlier. Well, we're not going to go into that, but attempts at converting general relativity into a quantum theory involves these spin to gravitons, which are different from the spin zero gravitons, which I will mention in my theory. So we have general relativity, and as coming from the Lorentz transformations because of this space-time concept, four-dimensional space-time. Now, I have shown previously that the Lorentz transformation, I showed us several tests, but I will list this again, 5 tests that the Lorentz transformations fail. It fails a one-way speed of light test. I have talked about using the synchronized clocks of the GPS to conduct this test, and they show that light speed for light traveling between 2 fixed points on the surface of the Earth, that light speed is not constant. So it fails that test. The Michelson-Gale experiment, because the Lorentz transformations actually predict constant light speed, it fails the Michelson-Gale experiment because it means that it predicts zero fringe shift in that experiment and cannot account for the observed fringe shift, the fringe shift that was observed in the 1925 experiment and all subsequent experiments of that type. They have talked about ring laser technology is the modern form of the Michelson-Gale experiment. Then the Wang experiment, which is like a linear Sagnac, where Wang had moving fiber optic cable and passed light in counter-propagating light beams around that moving fiber optic cable, and showed again that there was a difference in the time the light took to go around in different directions, and the Lorentz transformations cannot account for that experiment. Then there is the GPS clock synchronization. There is an equation published by Ashby which defines how the GPS clocks are synchronized. The Lorentz transformations cannot derive that equation. In fact, what is needed after you derive it, you can only get a part of the equation, and a correction has to be added because the Lorentz transformation fails in deriving the equation. So it fails that test. And finally, I would mention that the Lorentz transformations cannot accommodate superluminal signals, that is, signals that travel faster than the speed of light. What happens is you see that CV at the side, it means causality violation is what results for faster than light signals under the Lorentz transformations. So what has actually happened today is that all efforts are made by the scientific establishment to deny the existence of superluminal signals, but they have been published over the last many years of various situations of superluminal signals. So I am satisfied that they do exist, in which case the Lorentz transformations are falsified because causality violation simply cannot occur. So I'm concluding then that the Lorentz transformations fails these 5 tests and therefore are wrong and must be rejected. And as you know, the transformations I put forward are the celery transformations. Anyway, so moving along then, we're saying that the Lorentz transformations are invalid. Therefore, what followed from them, 4-dimensional space-time, the space-time concept collapses, means that it's simply not true that space and time exist as separate entities, if you like, and therefore that general relativity is wrong. And some of the predictions of general relativity now, which if general relativity is wrong, as I am contending, as a result of the failure of the Lorentz transformations, then it means the predictions are themselves going to generally, they cannot be accepted. We have to reject them all unless some other theory predicts them and you go and test. But for the moment here, the predictions which I would say have failed, it means there's no Big Bang. That whole theory of cosmology, so cosmology falls into question immediately. No black holes, no Hawking radiation, no dark energy, no Einsteinian gravitational waves. And I will come back to those waves because we know, LIGO has claimed detection of these waves and a Nobel Prize has been awarded and so on. So it deserves, since I'm claiming that they don't exist, I need to comment further on that, which I will do. What I will also say is theories of everything today attempt to combine general relativity and quantum mechanics. And if general relativity is wrong, then it means that to try to combine these two is not a viable proposition. So theories of everything, which in fact attempt to do that, combine quantum mechanics and general relativity, will fail because general relativity is wrong. So string theory, we all know it's for over 40 or 50 years they've been pursuing that. Not a shred of supporting evidence for string theory. Loop quantum gravity, which you might have heard about, again fails because it includes general relativity. There's a theory called E8 theory I've seen on the internet, and geometric unity and others. My contention is that they will all fail because they are trying to unify general relativity along with quantum mechanics. And if this is wrong, then such a unification will collapse. And that is my contention as some of the implications of the invalidity or my claimed invalidity of general relativity. So I therefore, coming out of all of that, I am proposing a new theory of gravity. And that's the connection, Ian, between my previous work and this. Previously, we're seeing that I'm saying the Lorentz transformations are wrong, and the Lorentz transformations led to a number of things, including general relativity. So since the Lorentz transformations are wrong, then those things that followed from it must fall into question, general relativity being one of those things. And therefore, I am proposing a new theory of gravity, and the equation that you see here it's a wave equation, which is box, and this box represents what's called the D'Alembert operator, which is this thing down at the bottom of the slide here. I've just put it there just so to remind you what it is. Equal to minus 4 pi g is the gravitational constant, and rho m is mass density. So this is the equation, and how did I come about that equation? Well, that will be for a separate lecture completely, but I use something called the gauge invariance principle, which was used to develop quantum electrodynamics and to put forward the idea that the quanta of the electric force are photons, and photons are virtual photons go back and forth between two electric charges that then result in the Coulomb force between those electric charges. If they are alike, they will repel. If they are unlike, they will attract. It's a similar idea, and that is as much as I will say about it, because it's a little bit technical, so we won't go into that today. But it is using that gauge invariance principle in a way not recognizing Lorentz, what they call Lorentz covariance, which is that the equations or laws of nature must take the same form when you move from one frame to another. Well, since I'm saying that the Lorentz transformations are wrong, I have relaxed that requirement of Lorentz covariance. And I talked about that in my presentation on superconductivity, where I relaxed it there, and I was able to come up with a new theory of magnetism. And I talked then about magnetons, which was spin 1 quanta that mediated the magnetic force, different from the electromagnetic force. Today, I'm saying, using that same gauge invariance principle, I've come up with this equation representing it really, and I'm comparing it with the field equation of general relativity, just for comparison purposes. And the equation I am putting forward is a gravitational potential. So this equation here is one linear equation for scalar gravitational potential A. And it's a wave-like equation, means that gravitational potentials propagate at the speed of light. That is what it means. Then using those results that I talked about under using the gauge invariance principle, I determined that the gravitational force is mediated by spin 0 and not spin 2 gravitons. Therefore, the idea of no more action at a distance, which is the criticism that is levied against Newtonian gravitation, that is this, instantaneous action, we can dispense with that criticism or that failing, because now we have converted the Newtonian gravitation into a full quantum theory involving the propagation of the scalar potential A, representing and from which you get the gravitational force. And if you look at the next slide, this equation here reduces to, for the static cases, to this equation here, which is Poisson's equation for static gravitational potential. This thing is del squared is an operator that looks like this down here, so the time component is out because there's no time variation. And this is well known. This is standard stuff in Newtonian gravitational theory. From this, you can get Newton's law of gravitation with the inverse square law, which is this. And that is why I say it contains 300 years of Newtonian gravitation, because from my equation, which is this equation here, you can get, all of Newtonian gravity that has been developed for the past 300 years, up to just before the time of general relativity, or a little before. So that is a first major test that the theory passes. If you're developing a new theory of gravity, it really needs to account for all of the established theory which is 300 years of Newtonian gravitation, and it does so, as we can see. So moving along now. Following the development of general relativity, there are several tests that were developed for testing that theory. I am listing 6 of them here: perihelion shift, gravitational light bending, gravitational redshift, Shapiro time delay, energy loss from a binary pulsar, and Titius law, which is the Titius-Bode law. I will say a little bit more about that, because that's not a test of general relativity. In fact, general relativity cannot account for this law at all. But I will come back to that. So, as Ian mentioned, if you have a new theory, the theory must make predictions which must then be tested. We have a lot of already conducted experiments, so a lot of information that we can use to test our theory, and this I'm listing 6 of them here. So let's go to the first one, the perihelion shift of Mercury. We know from the wave equation, my new gravitational wave equation, that the gravitational potential propagates at the speed of light. What has been known for some time is that retardation effects, as a result of the time to propagate that equation, for that potential to propagate, results in the retardation effects result in a changed force equation. So you go from F equal to G m over r squared to this term. There's this term here that is added as a result of the propagation of the gravitational potential. And this has been developed. There's a paper, I didn't put the reference down, by Asden, where he goes in to show how, because this idea that propagation of gravitational potential could account for some observed phenomena is not a new idea, and he had worked it out and came up with this equation as a result of this delay. Now, this is exactly the equation that yields the change in the perihelion shift of a planet going around the sun. And in the case of Mercury, 43 arc seconds per century was unaccounted for. I think the total amount is 570 something as a result of all the planets acting on Mercury's orbit, but only some of that was accounted for, and 43 arc seconds were not accounted for. And this equation is exactly the equation derived in general relativity. You will find this in the book. So the retardation effect as a result of gravitational potentials propagating at the speed of light result in this equation, which produces that shift of the perihelion. And of course, we are all familiar with this diagram where it's shifting as it goes around the whole orbit rotates around the sun, as it were. Okay, so this is pretty well established, and I'm satisfied that the new theory passes this test. Then there's gravitational redshift, that when as a result of a photon leaving a gravitating mass and moving away from the mass, it suffers a loss of energy. Now, this first equation is well known. The energy of a photon is Planck's constant multiplied by the frequency of the photon. And we also know that when light falls on certain substances, it imparts momentum to the substance such that it behaves as though it has a mass given by the energy of the photon divided by the speed of light squared. So photons under certain circumstances behave as though they have mass given by this equation. So when we use this equation and we work out the work done in a photon moving away from a body of mass big M, the photon of mass small m, we use this equation to work out the work done in going from a distance d to a distance d plus delta d, and we come up with this result, out of which we can then work out using the energy equal to Planck's constant times F to give us the change in the frequency, the fractional change in the frequency of the photon is given by, and when I work through this, I get this result where G is the acceleration due to gravity, delta D is the change in distance moved up from the surface divided by c squared. And this is well established in the literature and has been tested, and it results in accounts for the lowering of the frequency of a photon that is leaving the surface of a mass. So that's what I'm trying to depict here. These are all internet diagrams, of course, these images. So it will, the frequency of the photon would be lowered. So it becomes as it will redshifted as it leaves it. And this has been checked and has been confirmed experimentally. So that's test number 2, that the new theory successfully passes. Test number 3, gravitational light bending. I guess this is the one of the most sensational. This is the one that, caused general relativity to be so widely accepted after that 1919 expedition on measuring light coming from a star and the experiment that was carried out then. Well, this is the equation I told you results from the fact that the gravitational potential, there are delays because it takes time to travel from one point to the other. And when we use this equation and we apply it to the photon with mass, such as I've described, the energy over the light speed squared, we get a result for this bending. So our light traveling here, if we use this equation, we can work out, and of course, I don't show the full analysis, but this is a summary of the analysis. And we get that this angle here, the total angle, of course, is twice this, the way how I've drawn it, and we get that delta is equal to 4gm over rc squared, where m is the mass of the object, r its radius, and g is the gravitational constant, and we get 1.75 arc seconds. This has been confirmed in the literature. The experiments have been conducted which confirm that bending. And this is just another internet image showing that it's an actual position of a star. The light passes next to the sun. This is Earth, and it's bent by this angle here. And the star appears to be up here when it's really back here because of that bending. Okay, so that's gravitational light bending, and the theory passes this test. Going on now to Shapiro time delay. This was a test developed later after those first 3. By the way, I should mention, I didn't, I should have mentioned that the perihelion shift of Mercury, although it is attributed to Einstein and general relativity, it really was worked out back in, I think it was 1898, by Gerber. I'm sure many of you are familiar with that name. There are those who even claim that Einstein really took Gerber's work to come up with his own, but I don't know whether that is true or not. But what I am prepared to say is that Gerber came up with the formula for perihelion shift. He was the first to do so, and certainly did so well before Einstein, who published his work in 1915, and Gerber did his work in 1898. So the claims in the literature and the textbooks and so on that, Einstein was the first to come up with this result and to explain this perihelion shift, which was unexplained before, I think those claims are really not valid. All right, let me continue now with the Shapiro time delay. What we have is the sun here, S, a planet, or a planet over here at P, and the Earth over here at E. And we're talking about a signal, let's say, sent from the Earth to the planet and reflected back to the Earth. Passing near the sun, it experiences a delay as a result of, again, now this is the equation I have worked out, that the actual speed of the signal, light signal, passing next to the sun is given by the normal speed of light into 1 minus 2 gm over rc squared, where m is the mass of the sun, or whatever body that the light is passing next to. And r is this distance from a general point here to the sun. R is not, this small r is not the radius of the sun, it's this distance to the light signal. Now, the idea that to derive this equation, I use a fact of that photon flux density is proportional to the square of the frequency of the light. This is something I came across in one of Wesley's books. I wasn't familiar with it before, but in reading through his book, I came across that requirement and in fact was able to use it to derive this equation here, which shows that the light speed varies as it passes because of the gravitational action of the sun as it passes close to the sun. And when I worked through the analysis using a paper that I found online where somebody did something similar, his arguments were a little different, but the analysis helped me to derive the time delay for light going from Earth to the planet and being reflected back. This is the equation here. Good? Where g is the gravitational constant, m is the mass of the sun, and this is log to base e. And these parameters here, re is the distance from the Earth to the sun, xe is this distance from the Earth to this point here, and you have xp and rp. And when I was able to derive this, again, using this equation, which follows from the wave equation, the new equation that I've developed along with this principle that photon flux density is proportional to the square of the frequency. And when you plot the graph of the time of approach of how it goes, if I go back here, what happens is this planet is moving. And as the planet is moving, it passes behind the sun and comes out on the other side. And they plot the Shapiro time delay against the time as this traverses the goes behind the sun and comes out on the other side. So you hear that this time here, 0 is when it actually is behind the sun, and this is before and this is after. And when you plot the time delay, you get this curve represent, and you see that the actual measurements fall along the curve very, very nicely. And this is the paper that I used to help me with this, the Shapiro time delay and the equivalence principle. This author here, Purcell, he wasn't able to get my exact formula. He had to do some other things. If you read the paper, you will see. But his technique, I was able to use it to allow me to get the equation that I showed, which is this equation here, that represents the time delay of a signal that goes from Earth out to a planet and back to Earth and passing close to the sun. And what happens when that planet passes from one side of the sun to the other side. So you get this curve here, which is so well represented, and it's confirmed very nicely by the results that this author has put forward. So the Shapiro time delay has been passed. Of course, general relativity passes this test. There are some issues there, but I won't go into them. What is the point I'm making is that my theory also passes that test. Then, so that's 4 tests. Then we have the energy loss from a binary pulsar, PSR 1913 plus 16. This is a test that was done, I think, in the 1980s, where they said because of gravitational radiation, the argument goes, the pulsars which are orbiting around each other, the distance between them, if you like, will diminish because energy is being dissipated so that they will come closer together. So think of this axis here as them getting closer, and this axis as the times. This goes from 1975, 80, 85, 1990 up to 2000. And this is another internet image. General relativity predicted this, and the actual measurements fell along this curve very, very well. So again, if your theory is to be viable, you have to pass this test. Well, I ran into some fortune because I really didn't know how to approach this task to work that out. It turns out that B.F. Schutz, in a paper in the American Journal of Physics back in 1984, gravitational waves on the back of an envelope. This shows, you know, the American Journal of Physics tries to simplify aspects of physics so that for learning purposes of teaching and learning. What this author did, instead of using the full general relativity theory, which is, as we know, is very difficult, to simplify it, he chose this equation. This is why I said it's not a new equation, though he chose it simply to move from a static equation, which is the Poisson equation for gravitational potentials, to one that propagates in time, to give it a wave, to allow it to propagate in time. And he used this equation, which is exactly the equation, of course, that I'm presenting today. So in his paper, he did the calculation he used this equation, and he said he calls them back of an envelope calculations. In other words, they weren't entirely rigorous because they were not intended to be, but he still got the results to an accuracy of 10%. So this is an area needing further analysis and research. But the point is that the equation comes within 10% of giving the results that were published and observed for this binary pulsar. So I would say it passes the test to a reasonable level of satisfaction. Now I come to the sixth test that I'm going to talk about today. We will all likely have heard of the Titius-Bode law, which is a law which gives the positions of the planets in space relative to the sun. And it is, I haven't written down how it was first written down. I didn't write that down. What happened in 1913, this author, Blagg, published an improved form of that law, and that is what I have captured here, that the distance Rn to a planet is given by this equation here with 1.73 R0 into 1.73 to the power n. And this dotted line that you see on this graph is really, a plot for this equation here, showing that it represents the positions of the planets very well. Actually, the full revised relationship published by Blagg involves an additional term A, which is a correction to take into account this variation that you are seeing. It looks sinusoidal, doesn't it? But I am just dealing with the, shall we say, the average of that, which is the dotted line, which is this equation here, which is a geometric progression. And it's just a number representing the number of the planet as you move along. So that as you go from n equal to 0, you get Rn equal to R0, and 1, 2, 3, 4, and you get planets at each of those positions. Now, the thing about this is, this has been seen to be a general law of nature since, I don't know how many of you know this, but that law actually holds not only for the solar system, but it also holds for the satellites of Jupiter, the satellites of Uranus, and the satellites of Saturn. It's an amazing thing. And they all hold with this common constant of 1.73 in the equation that you saw there, where log of that is the slope of the straight line through the masses. When you write it like this, you see log of 1.73. If you plot log of Rn against n, then you get a graph of slope log of 1.73. And that equation holds for all of these four systems. So that has to be seen as a general law of nature and is not some accidental thing at all. General relativity cannot account for it, so you don't hear them talk about it, and it's ignored because it can't account for that law. And this reference I have here, the Titius-Bode law of planetary distances, is history and theory, is a very good book discussing the history of this Titius-Bode law and where it has gotten in the 20th century. Okay? And I do commend you to that book. It's a very interesting book. In fact, this graph came from that book. So the Titius-Bode law is there, unexplained. I now turn to Peter Beckmann. Some of you may have heard of him. He wrote this book, Einstein Plus 2. He was an electrical engineer at the University of Colorado, and he published this book. And in this book, he derived this equation. It is really quite an accomplishment in my view. Following the analysis, it's not exactly straightforward, but what his basic idea is that stable points where the aberration component of the gravitational force, as a result of, the gravitational potential is propagating, and there will be aberration components that are likely to tug the planet away from a stable position. Where those aberration components go to zero, then he considered those are the points where you will have stable planetary positions, such as we observe in the actual solar system and in these Uranus, Neptune, and Saturn. So he worked through that and determined, he saw the equation he used was actually, again, my wave equation. But he used it as applied to actual force and generated the result that you see here. This is what, if you read his book, you will see that he has this formula. I use the nomenclature I use here is to make it use just what Bragg used. So the only thing that Beckmann didn't come up with was the actual value of B. But as you see, the equation he generated was just exactly the same equation here, represented the dotted line through the planets, but not without the constant B, which, like the gravitational constant and many other constants, you had to determine experimentally. So I actually believe this should be called the Titius-Beckmann law, because he is the first one to ever have done such a thing and come very close to explaining, I think, a decent effort at explaining the positions of the planets and why this Bragg law holds true. Now, the new equation of gravity is essentially what Beckmann used, so it passes another test. This test, I am not aware that general relativity is able to derive this equation. So I think general relativity fails here. Now I want to turn to the Einsteinian gravitational waves, which LIGO claimed gravitational wave detection on September 14, 2015. They claim that it resulted from the merger of two black holes, about 1.3 billion light years away. The discovery was announced on February 11, 2016, and a Nobel Prize was awarded in 2017. Wonderful stuff. The world was excited by this development. This is an image of the laser interferometer gravitational wave observatory in the United States. One of them, each arm is 2 miles long, and really expensive stuff. Over $1 billion spent in doing this work. Problems with the gravitational waves that were detected. The discovery was announced exactly 100 years after the publication of General Relativity. After they've searched for so long, it just so happened that right on the mark of 100 years, they made this discovery. And not only that, it was discovered, it involves the merger of two black holes, which of course are singularities. So it's quite a coincidence that black holes, which I contend have not been experimentally confirmed despite all the claims, they got two of these unconfirmed objects coming together to give you gravity waves, which they couldn't predict which they couldn't discover or detect for 100 years. 100 years after the prediction of general relativity, you have this thing being confirmed. I find the coincidence was too great, but I'm moving beyond that. LIGO detected signal deep in noise. a team, I mean, they had to filter out noise. This is the signal was so tiny that they had to go through some real gymnastics to get the signal out of that noise. Well, a team led by Professor Andrew Jackson has raised serious objections to that. And this is the reference is there, is one reference, Grave Doubts About LIGO's Discovery of Gravitational Wave in New Scientist, where they talk about Professor Jackson's objections. And I don't think his objections have been satisfied to date. But here is so let me just go back up. So that you're not distracted by the last line. My main objection to gravitational waves, Einsteinian gravitational waves, is that the equations, which are linearized GR equations, so they took the original field equations, they linearized them. Those are the equations which they use to predict gravitational waves. Well, what is hardly ever mentioned, but known certainly among physicists, is those linearized gravitational waves, equations, also predict that there is no gravitational interaction between masses. Now we know gravity exists, but those equations predict that it doesn't, to put it simply. So what physicists have done is that the equations make two predictions. They make other predictions, but let us concern ourselves with these two. They pick one and reject the other. So they pick gravity waves and spend over $1 billion and years searching for them and claim detection now. And the other one, which is no gravitational interaction, which we know to be wrong, they have rejected that. Now, that's not how science is conducted. And for you to spend all that money searching for waves that were predicted by equations that have made an invalid prediction is very unscientific. And my own view is that the claim of detection of gravity waves is that this project had become too big to fail. They had to find something. So, and when you go into how they actually calculate, claim the detection, we don't have time for that today. But suffices to say that others have raised concerns about how they conduct their business. And as far as I know, it has not been independently confirmed. I think India is building one of these systems, and maybe they will check and see. But I certainly do not accept that this is true. And I contend that these gravitational waves that they have detected are unreal. That's just my position. So moving along from there, the new theory predicts Newtonian gravitational waves, which is the gravitational potential A propagates at light speed. That's all it is. And experimenters should search for longitudinal, because the solution of that equation, the wave equation will produce, because it's a scalar equation, will produce longitudinal waves as opposed to transverse waves of the Einsteinian type. The Newtonian gravitational waves would be longitudinal waves, and there is something called a superconducting gravimeter that measures acceleration due to gravity. I didn't know of these before, but in doing this work, I came across this. Well, I knew they were able to measure it, but there's this network of superconducting gravimeters as a detector. This paper is a good source to find out about this network of superconducting gravimeters that's being used to detect gravitational potential changes. I am suggesting that this network can be used and probably has detected these longitudinal gravitational waves, where a distant gravitating body and how it changes will influence the gravimeters and be recorded. But that's a whole line of research that waits to be done, which I suggest is viable. But I want to turn finally, as I come to the close, Ian, there's a major unsolved problem in astrophysics, astronomy and astrophysics, is what causes the rotation curves of spiral galaxies. And I seem to recall, I think it was Franklin did some work with ChatGPT on this. what we have is the velocities of the outer regions of rotating spiral galaxies, which is here, and these are actually measured, do not follow Newton's inverse square law with distance from the center, which is this. So this is what is observed, this line here, B, and A is what the theory says should happen. The velocity should fall off as you move away from the center of the galaxy. The major hypothesis that the main hypothesis that is used to explain this is dark matter, as we know, and it's something like this. The blue halo is like dark matter, so the spiral galaxy is immersed in this dark matter material, as a result of which the Newtonian interaction causes, the Newtonian gravitational interaction causes the outer parts of the galaxy to have velocities that don't fall off, that they continue to be high. That's the widely, I wouldn't call it accepted explanation, but certainly it's one that's on the table, and there's a major search for dark matter, as we all know. They haven't found it yet, but they're still looking. So here is a research program I am suggesting for interested non-specialists. This, I've written out here the full wave equation that I've put on the table this morning. Good, this is, instead of using this simple box A, I've written out the terms. So it's a single linear equation, and it's really easy to solve in general terms. It certainly has no difficulty like the equations of general relativity. So a suggested research program is to apply the new gravitational wave equation to the problem that we just described using AI, for instance, ChatGPT or DeepSeek. The basis is that at the large distances involved in these galaxies, the delay of the traveling gravitational influences would be significant and may affect galaxy velocities in a way that we don't know or don't expect. Remember what happened with perihelion shift? I mean, Mercury is much closer, it's close, the distance involved in the solar system are much smaller than the distance involved in the Milky Way galaxy, for instance. And yet the effect that we observe, we are claiming, because of the delay of the propagation of those gravitational potentials, resulted in the whole orbit of Mercury precessing. Well, who knows what the effect of those delays for much larger distances may be? And my hunch, or my speculation rather, my speculation is that that delay over such vast distances could possibly account for what is happening with those velocities of the outer parts of a galaxy. And I'm proposing, and really we don't have, in using ChatGPT, for instance, you are not carrying out the calculation. We're putting in this equation into the system and asking it to apply it to spiral galaxies. I have done that. Unfortunately, the results have been mixed. I remember in the early stages, I got some really nice results, and ChatGPT telling me this could possibly account for this problem. It really could. And that we don't need dark matter. But subsequent efforts said the effect is too small. So I want to invite others to participate in this bit of research. I would be delighted to hear from you on your results, and I've put my email address there if anyone wishes to communicate with me. But I'm saying we don't have to know how to solve that equation. We're just putting it into the AI system and asking it to apply it to solving the velocity rotation curve problem, or at least applying it to spiral galaxies and describing the problem and asking it, can this produce the result of flattened velocity curves for spiral galaxies? And I think it should be very interesting. So I want to end at that point, Ian, and just say thank you for allowing me to make this presentation. I think that the results that I have presented here, I hope I should say that I have given food for thought among the many participants in this program, in this group of researchers, and I hope to hear from some of them later on. Thank you very much. So Ian, you can come back up now.
I'm coming back now. Yeah, thanks. Shall I bring down your slides for the moment?
I guess you can. I don't know if people may wish to refer to something, but you could bring it down for now, and if we need to put them back up, we could do so.
Okay. And I think that's also got rid of the echo, because I think the echo is caused by my putting your slides up. It's a sharing system. It's sharing the audio.
Yeah.
So we got rid of that.
Sure.
Well, thank you very much, Stephan. As usual, you did not disappoint in any way at all. There was so much food for thought there. I just have a few little notes here, just maybe prior to addressing some of the questions and discussions that have come up. You've not only given us a fascinating insight into the work you've been doing, based on what personally I would say is rational classical physics, and you've also made a valuable invitation to all of us actually to participate in this project by using your sort of D'Alembert gravitational potential equation and applying that to spiral galaxies, which actually might be one fruitful way to use AI, because people are just popping things in AI bilio and just getting rubbish out and rubbish. But here we might just use AI to do a lot of the donkey work based on a very interesting concept.
Exactly.
So,
yes.
So thank you very much for that. Just maybe one very quick question first before some comments. One of your initial tests was that for the conventional LTs, the Lorentz transforms, I might have missed something. You said the GPS clock synchronization, they failed that. I didn't quite follow that how, because they claim in the mainstream that they don't fail it.
Actually, no, the mainstream doesn't claim that. The mainstream, if you look at Ashby's paper in Living Reviews, I think is the name of the journal, what they failed to do, the equation, they use general relativity to derive the equation that is used to synchronize the clocks. They use general relativity. And Ashby points out that if you assume constant light speed, which is what the Lorentz transformations predict, then you will get an error. You will not be able to synchronize the clocks. He recognizes that. So they don't ever claim that the Lorentz transformations can actually derive the equation to synchronize those clocks. And we could discuss that further, Ian, but that's simply a fact. I have never seen them claim that for the Lorentz transformation. But in my testing of the Lorentz transformation, I point out they can't derive that equation, whereas the celery transformations can derive the equation, and therefore the Lorentz transformation fail to be able to do that.
They might say, that in the absence of gravity, the Lorentz transformations would.
No, they wouldn't make that claim. No, because it has nothing. Its failure has nothing to do with gravity. Its failure has to do with the fact that it predicts constant light speed, and light speed on the surface of the Earth is not constant. They don't say that, but it predicts constant light speed, and you can't derive the equation for synchronization using constant light speed. I actually described that.
I see it now.
Yeah. Okay.
You're talking about clock synchronization. So it's basically, say, making a Sagnac correction for the spin of the Earth, which they cannot account for because.
That's how they explain it away, Ian, by calling it a Sagnac correction. But it's a correction, meaning I got it wrong and I have to correct it. That's what it means. But they've sold it so effectively as though the theory is fine and this correction is something that we just have to add, But it's a correction, means they got the answer wrong to start with and they have to correct it. That's what it means, literally, Ian.
Oh, okay. So just maybe one other thing, Stephan.
Yes.
Before we get to the questions, I may have raised this before, but you talk about the theory, I suppose, being equivalent to the conception that gravity is propagated. There's not like action at a distance. Gravity is propagated at a speed equal to the speed of electromagnetic radiation, say,
Yes.
in free space. So people like Tom von Flandern have quite a theory, and he has a number of experimental criteria which seem to indicate that the speed of gravitational interaction, as distinct from waves, would be considerably more. I mean, orders of magnitude more.
Yeah.
And you talk about the Gerber and so on. That's all very interesting. Yeah, indeed. But that equation, which is the same as the general relativistic one, which Einstein didn't acknowledge, but it's coincidentally coming up with this 43 arc seconds, which is the value which was widely accepted at the time, say in 1915, over 100 years ago. But
Yes.
I've looked at some information that seems to indicate that modern values of that are quite different. Anywhere from 39 seconds upwards. So that equation might be correct. And also the other one, sorry, I'm bringing them in at the same time, but you had the value of the light deflection of 1.75 seconds, which is twice the Newtonian value. Well, has that really been experimentally determined to the exact, the exact value? I mean, some research might indicate that is actually correct, and that the Newtonian value of 1/2 that is actually correct, and that we haven't been able to discriminate experimentally there. So sorry, I've put in about 3 things which are connected with the so-called proofs of general relativity.
I am going with the accepted values. I mean, if in fact it turns out to be wrong, then my gravitational wave equation fails. If it turns out to be wrong, then it fails. So I am open to falsification, just like the other guy, Ian. But the 1.75, I saw that in a later paper, and I think that's the accepted deviation. Certainly the equation representing the deviation is what they accept in general relativity. So if it turns out to be wrong, well, my theory fails just the same way, and I'm ready for that.
And I know that there's no more man than yourself who would be so handsome in acknowledging that. So thank you very much for that. By the way, I was actually quite flabbergasted by your very specific statement. I mean, you didn't come to any conclusion, but specific statement which I'd sort of had some feelings about for the last number of years, about the coincidence of this one. Exactly 100 years after GR, this this LIGO business, I was quite intrigued by that. I didn't know it was exactly 100 years, so there'll be much to discuss there. Well, let's just see, Stephan, if we can quickly go through the what have we got here? Recording. Yeah, I know it's just I'll go through the questions here quickly. A lot of these were as normal questions arising from your discussion as they were going on, but they were really discussions between people.
Yeah,
I noticed one. I'd like to bring it up maybe. Actually, maybe while I'm looking for it, because I can remember what it was. I think it was from James Ayrton. He noted. I don't know if you'd noted this, Stephan, that this 1.73 factor in the Titius-Bode law seems to be equivalent to the reciprocal of Euler's constant. Have you ever looked at that at all? And
the reciprocal of what? Sorry, Ian, I didn't quite hear.
The Euler constant is about 0.577. It comes into things like harmonic series and things like that.
I see. Okay. I'm not really familiar with it, Ian. That's why I didn't understand what you were saying.
Yeah.
Mm-hmm.
Okay. No,
So I've not made that observation, but maybe something to look at.
Okay. Fine. If we can pay you back in 0.0001% of what you're giving us,
Okay.
that would be delightful.
Yeah.
Okay. Yeah. Coulomb's law. Okay.
But Ian, may I ask you, what are your thoughts on that? The Titius-Bode law in the form of that Blagg has described and that Beckman has derived. What do you think about that law as it exists today?
Right. Well, my initial thoughts, I'm going to give more thought. I mean, your ideas are very thought-provoking. My ideas, maybe repeating what you said, is that the main physics books will say it's inexplicable. They don't even, as you said, general relativity cannot explain it, and they don't even say that. It wouldn't be very politic for them to say that. They say we don't know. It's maybe a coincidence or something. And you have correctly pointed out that it applies to the orbits of the moons of these planets as well.
Yes.
So it must be a law of nature. And I think you're right. And I think probably Beckman's, I mean, you were very generous to say we perhaps call it Titius-Beckman law. I think his analysis seems to be correct. And that's my initial thought anyway.
Yeah. Okay. Good. Yeah. Thank you. Yeah. I am fascinated by it, actually, really I am. And that it holds on all these other systems.
It ought to be just a coincidence to get this
yes,
straight
it would
line.
Be exactly.
Yeah. And Professor Hallam Bouteyev has just he's acknowledged Gerber's work.
Yeah. Okay.
He says one other thing, by the way. Just put it up here for a second. Weber is actually Newtonian. It was used by Ritz for Mercury precession. I think it's a misprint. I think he means Gerber.
Oh, okay.
Yeah, that's I don't understand it. I didn't understand when he was coming to Weber. Gerber is Newtonian. It's used by Ritz for Mercury precession.
Yeah. Gerber did use Newtonian gravity, but he assumed that it took time. He assumed that it propagated at the speed of light.
Yeah, that's right.
And he worked out, and he had the paper is rather lengthy. It's quite long, but it's very interesting, and came up with that result that they quote in the general relativity books today as coming from general relativity. But Gerber was the first to produce it, which was 17 years before Einstein produced his work.
Yeah. Einstein seemed to be a bit, rude even about it. He said, "Oh, he's only a school teacher or something." I wouldn't.
Yes, you are right, Ian. And he spoke derisively about Gerber and said his analysis is wrong through and all of that stuff. He really tried to discredit the man's work, but it's there for all to see.
Okay, and by the way, just the second part of Hallam's thing, I think it's probably Ritz or another misprint, maybe typing quickly, RITZ. Did Ritz have anything to do with that? Do you know? Maybe
I am not. I don't know about Ritz working on that problem, Ian. It could well be, but I know the major thing that Ritz is known for is that the light speed is constant, is relative to the source, and that has been disproven. So I have not really gone through much of Ritz's work beyond that myself.
Yeah, that's right. And we've been talking a bit about that in the comments actually by email. That's right. And also in Harry's Ricker's cosmology sessions as well.
Okay.
But I mean, so just maybe to wrap up on the speed business. What do you think of Van Flanders' arguments, and also say the condition that there is no aberration in regard to gravity? So he gives some experimental results that there's an aberration in light, obviously. So, for example, it takes about 8.3 minutes for the sun's light to reach us, and we have to allow for that. And the same with stars. But gravity seems to be instantaneous. So the force of gravity seems to be collinear with the instantaneous position of the sun, not where the sun was 8.3 minutes ago.
Yeah.
And that would indicate, he would say, that the speed of gravity is very, very much larger than the speed of light.
Yeah. I have seen some of his work, Ian, and the idea that gravity travels extremely fast. I have to say I can't. I was more persuaded by the idea that gravity has a finite speed of the speed of light. I was more persuaded because I was able to explain more things with that. So where he has used infinite speed to explain certain things, I have not addressed that. You know, I guess the two positions can't be correct. So I have gone with the one where I have found that I am able to explain more things. And that's why I have gone with that gravity propagates at the speed of light and not instantaneously. Now, it may well be that under certain circumstances, gravity can propagate rather quickly because it's a longitudinal wave, and, you know, depending on the medium, different things could happen. But his analysis and his work, I have set it aside for the moment because I just am more persuaded by it traveling at a finite speed, the speed of light. And as I said, it accords with many of the experiments that I have shown this morning.
Okay. And that's just another example, if I may say so, of your openness to all the evidence. My own view, I don't know if it's a bit of sitting on the wall, but I make a distinction between the speed of gravitational interaction and the speed of gravitational waves. And I would say that the waves, you know, and that might be what's determining, you know, your analysis, would indeed be etheric and would be dependent upon the properties of the electric and magnetic, you know, permittivity, therefore the speed of light. Whereas the other one is just an interaction, and that could be, you know, 10 to the power of 8 times the speed of light or something like that.
Yeah.
So I don't know. It might be something we could discuss further.
I guess. Sure.
So thanks very much for that. Now, I am... okay. They've just been talking more about what you've said about Gerber's. Hallam says substituting the result into Ritz's formula, it gives the general relativistic formula and so on. Okay, now let's just see. There has been a little bit of private chat. I think I've answered one or two, or attempted to myself, but we might be able to bring a few people up. I'll just see what's in there. I just closed down the general comments. There's one more from Hallam. I might put it to you, Stephan, before closing this part down. He says that Ritz's model is in the same framework as Ampere's force law and Weber's force law. Maybe Stephan is doing something similar to Weber.
I believe, well, Ampere's and Weber's force law, Ian, I think that relates to electrodynamics, as far as I know. And I have not done any work in terms of examining other formulae. I've accepted Maxwell's equations and the Lorentz force law, and that is what I have worked with. You know, so the answer is no. I have not examined anything to do with those force laws at all. Except I should say this: the Salary transformations have led me, when I transform the Lorentz force law from one frame to another, whereas special relativity using the Lorentz transformations, whereas they have the form of the law remains the same, where F is equal to is what, QE plus the term with the magnetic field and so on. With Salary's transformations, the form of the transformed law changes somewhat. And maybe down the road we could explore that. That is the single area where I have done some work on the Lorentz force law. That if you move from the the preferred frame to another frame, the law changes slightly. And in fact, I have used the change law to explain a phenomenon where an electric field was appearing, an electric potential was appearing on a circuit carrying a high current, which was unexplained by Maxwell's theory. And I propose how this changed force law could explain it, but that's a whole other discussion. So that is as much as I have done, Ian. I have accepted Maxwell's equations generally, except for this single instant where the celery transformation suggested something else. But I have done no work with Weber or Ritz whatsoever.
Well, I was just thinking of the analogy, because a lot of these expressions are analogous. And I think what they're saying is Ritz applied his work to gravity. And I think Hallam and Kurt say that.
I see.
So
well, I will note that. Yes, I will note that and have a look. Yes, this is why I always said to you that I enjoy these groups, because you learn new things. So I wasn't aware that Ritz did work on gravity. So I am going to have a look.
Well, I agree with that, and you know, it's very good to be open and to listen to all these comments.
Absolutely.
Actually, what I have said on a previous occasion, as you know, is it's a pity we don't have more sort of mainstream people who put the opposite view, because a lot of us we're very open people, but we think in a particular direction, not that we have the same theories. And I welcome people with contrary views to come on. So if we come to the chat, there's some chats. Let's see, James Keane has been making a few points, and I might, and Dennis Allen has treated the advanced Mercury differently. Okay, I think these gentlemen might speak for themselves. Are there any hands here? If not, I'm going to bring you gentlemen up. There's Denny. I think he's put his hand up. Hello, Denny. You've said Joseph Smolsky has treated the advance of Mercury.
Yeah, Joseph Smolsky is a Russian scientist. He used to be in Siberia. I don't know if he still is. Specializing in supercomputers. And he has just noticed that the sun rotates, and so it's not a perfect sphere. And if you take that into account and do a lot of computing, you get the advance in the perihelion of Mercury coming out at the end. And he is on ResearchGate, I think. You may, if you want to look him up. It's Smulsky or I can't remember which. Either ends in Y or ends in I. And this means that this explanation that Stephan has found for the advance of perihelion is not needed. Only Newton's law was used by Smolsky. And also the binary star dissipation was treated by Ron Hatch in his paper, A New Theory of Gravity, in 2007. And he concluded that gravitational radiation could not exist. It was electromagnetic radiation that was causing the dissipation. That was at the end of the paper, I think.
You're familiar with that work, actually, Stephan. Ron Hatch's work.
I have, yes, I've read some of his papers. That specific one that Denny's referring to, I may have read it a long time, but I'll go back to it. You know, you often have to go back, things you missed before, you may have forgotten, you go back and take a look again. So I will go back and look at his paper.
Well, the Ian Cowan, you, Ian, have indicated that redshift is not due to gravitation, but it's due to the fact that Maxwell's equations are being used and should be using Hertz's equations. And so that accounts for the redshift, because there's a dissipation term in his equations for electromagnetism, and consequently, after a long way, the wave, the electromagnetic wave that's light, loses some energy because of this very slight dissipation. And so, in short, it seems to me that Stephan erred in saying that he was going to ignore Van Flander's work on the grounds that he could explain more without it. I think that that's a mistake on his part because, all these things that he was mentioning, I didn't write them all down. There was just quite a few. Most of them, as far as I know, can be explained otherwise without trying to assert that gravitational interaction travels at the speed of light. When Van Flander did the math and pointed out that if that were true, the outer planets of the solar system wouldn't have stable orbits. They'd go off to planets would shoot off into
spiral out, yes,
empty space. Yeah. So I think you made a mistake when you decided that you were going to employ that equation for c being the speed of light. C may exist, but it would have to be tremendously larger than the speed of light. So that equation is not necessarily wrong, but to treat the velocity of propagation as c seems to me to be counterindicated by Van Flander's calculations. Also, as far as the LIGO gravitational wave detection, that's been refuted by people like Richard David Scott, a former astronomer in Hawaii, and Johann Freemery, and some other people on ResearchGate. And Kagra, which is also
a gentleman that I've forgotten, but Stephan mentioned some other professor, Jackson or something, was it?
Yeah, Jackson, yeah.
Oh, I don't know about it. I haven't read it.
Yeah, he's actually published a paper objecting.
Okay.
Yeah, Kagra, which is also tries to detect gravitational waves, doesn't get any. And the thing about LIGO is that it's huge. There's people all over the world on the payroll, as it were, and getting papers, their names on papers. It was, I think Stephan mentioned, it was too big to fail. I think
right.
That's quite correct, Stephen.
And this 100-year coincidence is quite interesting.
Yeah, that's suspicious too, but people who believe in general relativity will say, well, it was just the way it is. It had to be some
right,
year. It just happened to be 100. But to me, it's suspicious. And David D. Hilster has pointed out, as far as dark matter is concerned, that the real problem is that when they analyze lens-shaped galaxies as opposed to spherical shape, the spherical shape, they take all the mass to be located at the center of the sphere and use Newton's gravitational law. But they try to do that in lens shape too, to saying that all the gravity is located at the center, and so you should use Newton's law for one point at the center. But since it's lens shape rather than spherical shape, that doesn't work right. David D. Hilster has a short video on that, saying that the real problem is that they haven't calculated the force of gravity properly in lens-shaped galaxies, because they assume, just like spherical-shaped galaxies, the masses all can be treated as a point at the center of the galaxy. Whereas in lens-shaped galaxies, that doesn't work at all. For example, in our solar system, it's sort of lens-shaped. The planets are in a lens shape. And they would never do that same thing for NASA, planets. They use Newton's law, right? But they don't assume that everything can be viewed from a point at the center of the sun, because they know, well, it can't. But here again, it's a political thing. A Nobel Prize has been awarded. David shows a picture of the guy getting his Nobel Prize in the video. And the whole thing is a scam.
Yeah. And by the way, I may be mistaken now because I wasn't able to get the references. But you mentioned, Stephan, that with regard to the deficit in the the what's it called, the perihelion shift. Yeah, you thought it was of the order of 500 altogether, or seconds when you take the planets into account. But I seem to remember that is from the point of view of an observer on the Earth. I think if you were on the Sun, it might be more like 5,600 or something. But whatever. I think there is a suggestion, let's say, that the small discrepancy, whether it's 43 seconds or whether it's 39 or whether it's 53, is so small. It's really a very small fraction of the total, and it may not be meaningful. If you take errors of observation into account.
Yeah. Well, if I could then just yes. So I agree with you, Ian. I as I said, if it is that it is wrong, and by the way, I think the planets account for 530 something, but they measure 570 something, and therefore there was 43 excess that they couldn't account for, something like that. I think I said it incorrectly the first time, but so whatever it is, well, we follow the observations and we see how that develops. I want to respond to Denny. The Van Flanders' idea that gravity travels very quickly. As I told Ian, I am going to look at his work. I saw that somewhere. I think it was in a paper he published. But you have to make a choice. You can't reconcile very fast, infinite speed or near infinite with speed of light. They're just widely different. So I chose to use one. You say I made a mistake. Well, it's a choice I made, and I have gotten some good results with that choice. But I certainly am prepared to go look at Van Flanden's work, given the comments that you're making, and see where that leads. Okay? So that's how we do the nature of research. You take a direction and you see how it goes, and then you get more information. You have to evaluate that additional information. So that is what I will do with your comments, Denny. So thank you for that. On the matter of, you mentioned tired light or loss of energy. I don't think that could apply as an explanation for what happens based on the experiments that have been done for light leaving the surface of a mass. I think there's enough experimental evidence supporting the idea that it's a gravitational effect that is causing that. However, I am in agreement with the idea that the redshift that they used for the Big Bang, that Hubble's law thing, I certainly believe that is a tired light phenomenon, in that as photons travel over long distances, they lose energy. And I saw an analysis by a fellow named Professor Monty, I think is his name, where he showed that if you take into account conductivity, apart from the permittivity and the permeability of space, if you take into account some level of conductivity, very small, very, very small, but you include that, then the solution to Maxwell's equations actually gives you a loss of energy without blurring, by the way. There's no, blurring of the image. When you try to explain tired light phenomena or explain the redshift on the basis of tired light, they say you have to explain, you don't get blurring. Well, with this approach, where you take into account a small conductivity of space, you actually get a loss of energy as a solution to Maxwell's equation. And I think personally that is a far better explanation of the redshift that we have observed than this idea that planets are moving away at high speed. So if that's what Ian has proposed, I'm in agreement with loss of energy on the basis of long travel to the cosmos. But I think there's enough evidence to support the idea that gravitational occurs. Yes, yes.
Yeah,
Ian.
I'm certainly very interested to hear that response, because I'm sure that's what Denny was referring to, because that is basically equivalent to the work I've been doing
I see.
as well.
Okay.
And by the way, Harry Ricker will be having a presentation, I think, tomorrow, talking about this very subject on the cosmology sessions, just to let you know that.
Okay. Okay. Yeah.
I don't know if he's here. He probably is here, and he may come in, but I don't see him in the green room. Okay, Denny, thank you very much for all those stimulating points.
Yes.
Anything else before we move on? Is that all, Denny?
Well, I think that the big problem in gravitational theory is that while Newton's theory is used very successfully by NASA to travel around the solar system and so on, very successfully, it does have an Achilles heel, and that is that the gravitational constant capital G, which was in Stephan's equations too, can't be calculated experimentally to more than 4 or 5 digits, when it should be able to get 8 or 10. And that indicates there's a missing variable in it. And that missing variable, according to Morton Spears, his article in Galilean Electrodynamics, and he died before he could finish up. So I wrote a book finishing it for him. Can you see that?
This is like the capacitive effect you're talking about, aren't you, Denny? We have a sort of a capacitive effect.
Yeah, capacitive theory of gravity. Yeah. Which comes from Coulomb's law, of course.
Okay.
And
I'm not familiar with it.
then you should be able to calculate correctly if you take into account the dielectric constant, or as I say nowadays, the permittivity of surrounding matter. And there's a whole book written. Can you see that? Can you read that?
What's the name of it, Denny?
Yeah. That looks like John Chappelle or somebody.
Laws of gravitation be edited by Hector A. Munera. Should the laws of gravitation be reconsidered? And it's the scientific legacy of Maurice Alias.
Okay.
Yeah. And what they do is they treat eclipses is where the problem arises, because then from a viewpoint of a capacitance theory of gravity, you have to worry about the capacitance of either the moon that comes between the sun and the earth, or the earth, which is between the sun and the moon and then causes an eclipse of the moon.
Did they look at some strange effects on a pendulum during eclipse? There were strange effects on the pendulum bob during an eclipse. I think Elias was doing some work on that.
Yes, and they have a number of different mechanical devices which they call amplifiers. In that, the key concept is unstable, stable equilibrium. I mean by that is, if you have a new penny, you can balance it on a perfectly flat surface and it won't fall over. But any little thing, so technically it's stable in stable equilibrium, but any little thing will knock it over, so it would be unstable, stable equilibrium. And that's what they do. They come up with these mechanical devices, about 90% of the book, and they during an eclipse, they behave strangely, and they amplify the effect that's being observed. And so I contacted some of the people in this book, and pointed out that Spears had an electrostatic theory of gravity, which I had to complete because he died, and he did all the heavy lifting though. And they said, "Well, good, but how can this help us?" And I said, "Well, it's hard to see because no one knows what the dielectric constant of the Earth is, or what the dielectric constant of the Moon is, or what the dielectric constant of the Sun is." And there's no, for example, the Earth, we know if you go down very far, it gets hot really hot. And so they say that it must be a molten interior. Well, under tremendous pressure. Well, what is the dielectric constant of that? Well, who knows? They don't even know why the North Magnetic Pole is now not over the Arctic Ocean, but it's over Siberia. It's moving at quite a large rate. And this, of course, affects the weather because the magnetic field of the Earth is what guides the particles from the sun into creating the weather. And for example, 3,000 years ago, the Sahara Desert was believed to be a lush green area. Now it's bone dry. This is, they think, because of that the Earth's magnetic system has reversed in past epochs. And so I wasn't able to give them much help with my with Spears' electrical theory of gravity because they don't know either the dielectric constant of the moon, the sun, or the Earth. So, but if someone ever came up with a good theory of what is inside of these planets, the Earth, the Moon, and the Sun, then you could calculate the dielectric constant and check to see if Spears' theory is right for eclipses, which behave strangely. These devices do not indicate that Newton's theory is right.
Something, Ian, that I have thought about myself, but I've just hadn't had the time to address it. But that area is a very fascinating area, the whole thing with eclipses and so on. So I am aware of that and we'll look into it. Yeah. Thank you, Danny.
Thank you very much for reminding us of all those important aspects, Danny. So we'll perhaps move on if we may. Thank you again, Danny. It's very good. Now, I think James Keane actually raised a few things. I think, well, he was asking, is there any unique data which could confirm your theories and so on? Jim, could I bring you in just maybe to raise one or 2 points you put in the chat here directly with Stephan?
Well, I'd like to thank Stephan for a wonderful presentation. There's a whole lot of material in there, and I applaud his adherence to the scientific method, which is very, very welcome here. One of my questions was you presented many different things. Could you summarize for us, or what is the main data which supports your theory and distinguishes it uniquely from other approaches, so that we can include your theory and exclude others? You see what I'm saying? Not data that multiple theories might predict, but what you predict uniquely.
Okay, that's a reasonable question. First of all, I had to test the theory. The thing to do is test it with known information. Good. So you have to pass all the tests that the other theories pass. So the main other theory, or the main existing theory, is general relativity. So you have to test it against the things that general relativity has passed. If you fail any one of those, then you're in trouble. So you got to go away and come back again.
But why is that? Because general relativity has been discarded and discredited already. Why? So I don't understand that first criteria.
Right. Let me explain it then to you, James. It is the accepted theory. Whether you like it or not, whether I like it or not, the fact of the matter, the scientific community embraces general relativity. That is a fact of life.
But that's a sociological statement.
Just now, let me explain. If we don't want to just be talking to each other, but we want to influence the scientific community, well, we have to do the things that they expect, which is you got to meet the test that general relativity passes, because general relativity is the accepted theory of gravity. So it passes certain tests. You have to pass those tests too. If you don't, they will throw it out, James, and you will just be talking to yourself and maybe people like you who agree with you. I want to move beyond that. So I have the first 5 tests I indicated: perihelion shift, redshift, light bending, Shapiro delay, and the binary pulsar decay orbit. Those are 5 tests that general relativity passes. So I have to pass them too, and I do. Now, here's the answer to your question. The one that I pass that general relativity doesn't pass is the Titius-Bode law. They fail miserably, and that, in fact, they fail so badly they don't mention it at all. Yeah. And I think my equation to Beckman's work allows me to explain that. So that is one area where I think I could identify my theory as opposed to the other. Yes, James.
So the Titius law is the one that you uniquely. Oh, okay, great. Yes. I had another question here. I'm scrolling up to see what my questions were. Why is time used as the 4th dimension in the gravitational wave equation in your last slide?
It's not a 4th dimension. It's just using the normal way of space and time as we accept it. Think of it as a Newtonian way, as a matter of fact. Okay. So it's just that's the normal way, James. I don't do the 4-dimensional Minkowski stuff. No, I don't believe that. I think time is separate from space, and they maintain that in the wave. That equation is a general wave equation that they use in a whole number of instances, and I'm arguing that it applies for gravitational potential propagation as well.
Okay, thank you.
Okay.
Okay, I guess that's the last thing that I might raise is this whole idea of gravitational lensing. Yeah. I think the word gravitation can be simply dropped, and it's just lensing. We have various energy density. We know that light can bend as it transverses from one energy density area to another. And there's, the term gravitation doesn't add anything to that, I think. In fact, as far as I know, the only real definition of gravity is the acceleration of objects in a energy density gradient.
Is this more than a use of a mainstream term then, Stephan?
I'm sorry?
Gravitational lensing, is it no more than the use of the term used by the mainstream?
Yes, they use it. Yes, and I see it. What James says, there's merit in what he's saying, that energy density effects could cause that bending as well. So that is one effect I haven't looked into specifically. I have classified that under the whole light bending phenomenon, and since I can show that light bends by the 1.75 arc seconds, I have settled for that. But gravitational lensing or lensing, James, is an area that I have to explore still. I haven't done any work there whatsoever.
Okay. The gray satellite data that I analyzed showed that, which was based upon special relativity, general relativity concepts. I actually debunked general relativity completely, because it turned out that the gray satellites were basically measuring ocean surface temperature, which of course is in agreement with binary mechanics. So I have to question I realize that, from the social engineering point that you mentioned prior, which I accept as some validity to that. From the scientific point of view, I have to question a theory which strives to meet criteria that a discredited, excluded theory, which my work alone, not to mention work of other people, has excluded, is really the way to proceed. I guess that's an editorial comment, which there's probably no real answer except another editorial. So I apologize for that. Stephan, thank you. You're a brilliant mind. I really respect your work, and I wish you all the best, sir.
Well,
thank you very much, James. Thank you. And Ian, if I might just comment quickly on the last thing he said. Thank you, James, for your very kind words. I appreciate it very much, and I appreciate your work as well as all those who contribute on this site. I really look forward to getting information and hearing these different ideas. So thank you, James. Yeah. So I wanted to say, Ian, about what James said. Why do you want to now satisfy as it were, tests done on a discredited theory? The thing about it is this, Ian, whether the theory is true or false, if it makes a prediction and you go and you test the prediction and you find that it turns out to be true. So you have a formula for perihelion shift and you test the perihelion shift and you see it matches up. Then what you have is a correct formula, but you may have arrived at the formula incorrectly. Right. So you know that there are wrong theories that make correct predictions. The Lorentz transformations make a number of correct predictions, even though I am convinced the Lorentz transformations are wrong. So too general relativity. It makes some predictions which turn out to accord with nature. So while I am prepared to throw out general relativity on good grounds, those tests or predictions is made that matched up with, that accord with nature, I preserve those so that my theory must meet those, Ian. So James has it slightly incorrectly. Slightly, and I say that with all due respect to him. What he should be saying is not that I'm testing it against general relativity, but I'm testing it against tested formulas for predictions that turned out to be correct, even though general relativity may be wrong. So that's all the tests I have listed there are tests where they have performed actual experiments and the predictions accord with observation. That's what I'm using, even though I'm rejecting general relativity. That's how you should see it. And that's what I put forward to him. Thank you.
All right. I quite see the distinction, Stephan. So thank you very much for explaining that.
Okay.
Now, Jim has acknowledged that as well. But now we're running very rapidly out of time. I see David, I'm not sure if you pronounce his surname Boer, has made a number of points. If you wanted to come in, David, maybe on one of those points, we would have time. If you want to raise your hand.
To hear him. I'm seeing his comments here, Ian.
Yeah, he's made a number of good points. He's made about 4 points, and we don't really have time to deal with them. But David, is there any specific point you'd like to raise? I know you've raised points.
Can you hear me?
Yes.
Dr. Gift, excellent presentation. Second only to mine. No, just kidding. Just kidding.
Good one.
My son is a majoring in electrical engineering at the University of Central Florida. I wish you could be one of his professors. But anyway, one comment and one question. Can you explain how you go from a continuous field theory to one involving particles, one that is mediated by particles? Maybe you could just supply a reference or an article that explain. I really don't understand how you put these quantum particles in.
Yeah, that's a very good question. And I didn't touch on it at all because what I have done there, David, is I have simply used the literature on that. So there's a book called Theory of Elementary Particles by what's the guy's name? I will look for the reference, in which he discusses how you interpret a field equation and explain its action in terms of the exchange of particles. That's not my area at all, and I didn't know about that before, but his book, and let me just quickly see if I could get that reference for you in my notes here. His book allowed me to make the statement. I his name is Roman. I think it's Paul Roman, Theory of Elementary Particles. It's a book published in 1960. I've never seen another book like that book. It's an old book.
Roma or Roman?
Roman, R-O-M-A-N.
Okay, thank you.
I think his first name is Paul. It's P. Roman, Theory of Elementary Particles, published by North Holland Publishing Company in 1960.
I just want to give you one little anecdotal story. Back in the early 70s, when I was in the U.S. Navy, I visited a professor at Lawrence Berkeley Laboratory. I was stationed in San Francisco area. I went to visit a professor at Lawrence Berkeley Laboratory, Radiation Laboratory, to ask him this question. I said, how do particles mediate forces? And he was, I can't remember the professor. I think it may have been Jackson, but John David Jackson.
Yeah.
But don't quote me on that because I don't want to slander his name.
Yeah.
But I asked him, how do particles mediate these forces? And he could explain how particles could provide repulsive forces by banging off, but he couldn't explain how they provide attractive forces.
Yeah.
Anyway, I want to make a comment before I leave. Back in the 70s, when I was an undergraduate, and in graduate school, I studied physics. And I vaguely remember in discussing classical mechanics that there was a theorem that if you have a central force that's not propagated with instantaneous velocity, that causes perturbations, or rather, what do you call it?
Oscillations.
Not oscillations, but perigee advance. It causes the perigee to revolve.
Precession.
Oh, precession.
Yes. If you have a force which is not instantaneous, it causes precession. And it's very vague in my mind, that theorem, but I want to reinvestigate that. But I think that is one thing that people need to remember.
Well, that fits in actually, David, with what I have read and the ideas that I depend on, that because I'm proposing that the gravitational potential is not instantaneous, but propagates it at a finite speed, then what you're saying, it causes that effect. And really, that's an interesting comment, because it accords with what I have become familiar with in the literature and what Gerber, back in 1898, he worked on that basis, and he worked it out, a long paper, and came up with the precession that we accept today. So that's a good comment.
There's another factor which no one discusses. There's a big controversy about whether mass depends on velocity, and there's a tremendous controversy. But if it does, that would also, just the special relativistic effects would affect the precession. Mm-hmm. If the mass does change with velocity. And Simon, in his mechanics book, assigns a problem where you do check the effect of the mass on the precession.
Okay. I've dealt with that mass change in my work with the Celery transformations and reproducing effects in special relativity. But in gravitation, I didn't see mass change as featuring a whole lot. So I haven't looked at it from that perspective, but I certainly have at the level of special relativity. And David, you may not know, but I am actually not proposing, I've embraced a theory which is called the Celery transformations to replace the Lorentz transformations, which I believe to be wrong. And Celery had published these back in 1995. I have tested them and I believe them to be correct. So that's what I just thought I would put a little plug in there for that to you.
Thanks for your excellent lecture. I appreciate it.
David,
Thank you
I
very
see
much, David.
you had asked earlier for Stephan's email, and we gave it to you a number of times. So you're welcome. I'm sure Stephan would be delighted, if I may speak for him. Contradict me if not. To receive anything further, because I think you've talked about Lagrangian and Hamiltonian mechanics, and if you want to put any of those further points to Stephan, we could deal with
I'd be happy to.
Thank you very much for your contributions.
Thank you
again. And 32 further comments have come in on the main email contributions, so we don't have time to deal with those, unfortunately. But Stephan, sorry for rushing it at the end, but what I'll do as normal, you may have said everything, the questions may have dealt with all the aspects you wanted to look at, but on the other hand, maybe one or two things have arisen following the discussion, and you may want to highlight one or two things in the talk that you gave us. So I'll give you a minute or two to summarize if you wish. I'll disappear now.
Sure.
And then I'll come back to finish. So the floor is yours again, Stephan, to finalize.
Okay, just to close by saying that, well, first of all, thanks for the opportunity to present and to speak to this audience. As I mentioned to Ian that one of the reasons I stay in these groups is because I get new information, you learn new things, people come up with different ideas, or they have new books that you didn't know about, or even old books that I just never came across, and papers and new ideas and new interpretation of ideas. So I find it very, very useful to be involved in these discussions. So I appreciate that greatly. I close by saying my quest, though, is a search, as many of you are, a search for truth. So this is why you would see me constantly trying to present something that, in fact, is better than what we have before. And I think I've done that best with the celery transformations. I really do believe they are correct. And I hope to say something more about the celery transformations and where I have taken them on this forum in the not too distant future. So thank you all for your interest in my work, and thanks, Ian, for the opportunity to present. Thank you.
Well, our sincere thanks are due to you, Stephan, because we do get many talks that are interesting, but there are few that can vie with yours in terms of being open and whilst not being too dogmatic and laying down the law and just stating, dogma arising from one's own experiments on the one hand, and on the other hand, being too pugilistic and just wanting to take on the world, take on the mainstream and start arguments with them. You've been a very open researcher. You're open to criticism. You're open to information to be obtained from other colleagues here, other researchers, and you're obviously very open to giving us the valued results of your own experiments and analysis, and they have been very cogent. I mean, for my part, I cannot fault any of your propositions in terms of cogency. I might not agree with everything you say. I might have different slants on it, but you're a totally logical thinker and expositor, and that's all we want. And if I may even say so, after the long session today, we might even value you back in the not too distant future to see some further aspects of your research, because all the talks we've had from you have been fascinating, and I'm sure every one of you will agree. So to wrap up, I'd like to thank the people in the social media for all your comments, all the scores and scores and scores of comments. And, there were maybe only a handful of them that we could deal with in the Q&A, but I hope we didn't disappoint too much in that regard. Anyway, you have Stephan's email, stephangift@hotmail.com. If we haven't dealt with any of those aspects satisfactorily. And to the people in the green room, I'd like to thank you very much. Stephan's talk today obviously prompted a lot of conversation, because sometimes we're a little bereft of that. But Denny made quite a number of very interesting points, and so did Jim, and so did David, who isn't normally in our green room. So thank you very much for that. Didn't get Vladimir in today. I might talk to him tomorrow about this and have a bit of a post-mortem. But last but not least, I'd like to thank again our speaker. He's been very generous in his time. He's been unstinting in making very precise overhead projection slides that we can read to follow. He's been very clear in his exposition and his answering of any of the questions. So thank you, Stephan, again. And I'm going to end this stream now and wish you, wherever you are in the world, I think almost everybody, with the exception of me, and maybe Roger is in the background there giving some links to the book by Roman. I'd like to wish you all a very good day. Goodbye.